Hello everyone, welcome back to the Nuclear Criticality Safety Lecture Series. Today we're going to discuss the TSURFER Experimental Data Assimilation or Data Adjustment method, which compares the observed benchmark experiment measurements with the calculated results from modeling and simulation codes to calibrate nuclear data. As we'll see, this method can be used to estimate something that is analogous to upper subcritical limits. Let's say that we have the result of a benchmark critical experiment and the result of a high-fidelity Monte Carlo eigenvalue simulation. As you can see, these two results are slightly different, which is because of the computational bias in our modeling and simulation code. Since our code is a high-fidelity Monte Carlo code with a minimal method bias, and since the fundamental theorem of tsunami states that errors and uncertainty in nuclear data are the main drivers for computational bias, then in theory, we should be able to adjust our nuclear data in a way that causes our simulated k-effectives to agree with our experimental k-effectives almost perfectly, or at least to within the bounds of the experimental measurement's uncertainty. This graph is just considering one experiment, so it's unlikely that wiggling the nuclear data until the two results match up will result in any meaningful nuclear data adjustments. But as we consider more and more experiments, our nuclear data adjustments will evolve our nuclear data to the point where it causes our simulations to exactly predict the eigenvalue of every system imaginable. In other words, if our training set is an infinitely large library of benchmark experiment results, then we can adjust our nuclear data to its true values. If we then take this adjusted nuclear data and apply it to our application system, then it will change k-effective for the application. This new, or adjusted k-effective, is a good stand-in for the experimental k-effective for that application, and the difference between the adjusted and the original calculated k-effectives is an approximation for the computational bias for that application. On paper, this method might sound too good to be true, and there are several challenges that it must overcome. First, how do we predict the impact of nuclear data adjustments on our benchmark experiment results? Resimulating the thousands of benchmark experiments in our libraries while we wiggle the tens or hundreds of thousands of nuclear data parameters will result in an impossibly long runtime. Fortunately, computing sensitivity coefficients for these systems allows us to estimate the impact of these nuclear data adjustments instantly. In fact, the data adjustment method that we use simply solves for the set of optimal nuclear data adjustments using these sensitivity coefficients. As I mentioned earlier, nuclear data uncertainty has a predominantly first-order effect on eigenvalue estimates, so adjusting our nuclear data using first-order sensitivity coefficients makes a lot of sense. Likewise, once we have a set of adjusted nuclear data, we can use the sensitivity coefficients for our application to predict how these data adjustments will change the application's eigenvalue. We don't even need to resimulate the application. We can just use the sensitivity coefficients to instantly predict the adjusted k-effective. So how does this magical experimental data assimilation method work? The algorithm behind this method, which is called the generalized linear least squares method, starts by defining a discrepancy vector, chi-squared, which is a combination of the differences in our calculated and experimental eigenvalues in terms of their number of effective standard deviations, and the changes that we're about to make to our uncertain nuclear data, where alpha represents our nuclear data parameters. These nuclear data changes are also expressed in terms of their number of standard deviations. By combining the discrepancy vector with the eigenvalue sensitivity coefficients for all the benchmark applications, and with the C over E's for all the benchmark applications, GLLS then solves for the optimal set of nuclear data adjustments that minimizes the discrepancy vector. From here, we can use the sensitivity coefficients for our application to predict how our delta alpha changes our system's eigenvalue estimate, which we now call k-adjusted. The computational bias for our application can be estimated by taking the difference between the original calculated eigenvalue and the adjusted eigenvalue, which again stands in for the experimental eigenvalue. This explanation actually simplifies how GLLS works. In reality, the uncertainty in nuclear data contains correlations between different nuclear data, and there may also be correlations between the benchmark measurements. And so, computing this chi-square discrepancy vector actually requires some matrix algebra to account for these correlations. GLLS is a Bayesian adjustment method, and you might recall that any kind of Bayesian adjustment actually has the side effect of lowering the uncertainty present in our data. For those of you who are watching this lecture who aren't experts in Bayesian statistics, another way of thinking about this is that by comparing the simulation results with the benchmark measurements, we add more knowledge than we previously had to our system, which has a side effect of lowering the uncertainty in the nuclear data. Thus, this data adjustment or data assimilation process results in a covariance matrix for the adjusted nuclear data that will actually always be smaller than our initial covariance data. Whatever uncertainties remain within our new adjusted covariance data represent the nuclear data uncertainty that could not be validated away through comparisons with the benchmark measurements. This adjusted covariance data can highlight gaps in our benchmark measurements, and with enough quality measurements, we should theoretically be able to reduce the uncertainty present in any piece of nuclear data to 0. So how does the TSURFER method compare to the other USL methods? One main advantage of GLLS is that every single benchmark experiment contributes to this data adjustment. In essence, TSURFER learns something about how to adjust the nuclear data from every experiment that it sees. This comes in handy if you have a lot of benchmark experiments that are only somewhat similar to your application, but none that are highly similar. This is also important for mixed oxide systems. We haven't performed many critical experiments using MOX fuel, but we have a lot of pure uranium and pure plutonium benchmarks. TSURFER can learn how to adjust the uranium cross-sections from the uranium experiments and how to adjust the plutonium cross-sections from the plutonium experiments, and then it can combine these adjustments to adjust the cross-sections and to predict the bias for our MOX application. Another advantage is that since TSURFER just uses every benchmark experiment, then that means that it doesn't rely on any specific similarity metric for determining the similarity between a benchmark and the target application. The C sub k similarity metric is pretty rigorous in its ability to predict the similarity between a benchmark and an application, but avoiding similarity metrics does avoid questions about what similarity metrics to use, how many similar experiments we need to include, or what to do if the covariance data changes and thus changes the similarity coefficients used in our trending analysis. Speaking of changes to the covariance data, how do changes to the covariance data affect the TSURFER bias estimates? Studies by Perfetti suggest that TSURFER bias estimates are relatively insensitive to changes in the covariance data, which is another huge positive in favor of these methods. Clearly, I'm a fan of these methods, and personally I feel that they are perhaps the most mathematically rigorous approach for estimating computational biases. However, these methods are not perfect. Most of the community's issues with the data adjustment methods are issues that we could address, but that we haven't studied in enough detail to address just yet. Some disadvantages to the TSURFER and GLLS methods that we must consider include: Number 1. How do we detect any benchmark experiments that are outliers? The scientists who perform these benchmark measurements are very hardworking, very careful, and very good at what they do. But when we're considering a library of benchmark experiments that was grown over the past 70 years, it's very likely that some of the benchmark measurements will contain errors, that some of our computational models might contain errors, or that we may have simply just entered the wrong number somewhere along the way. We need to be able to detect these errors so that they do not corrupt our cross-section adjustments. And fortunately, there are several methods for detecting outliers in TSURFER. The most rigorous of these methods, the delta chi-squared method, looks at how much each single experiment contributes to the chi-squared discrepancy vector and chooses to omit any system that contributes too much to this vector. In essence, it omits experiments that dominate the data adjustment process. This makes sense, since if we have a large number of experiments that all benchmark different pieces of the nuclear data, then each experiment should contribute a roughly similar amount of information to the data adjustment process. Any one experiment that requires things to be adjusted too far in any one direction is likely to contain some errors in its benchmark measurement or in its computational models. Another downside to the TSURFER method is that it requires covariance information for the benchmark experiment measurements. In other words, we must know to what degree the benchmark measurements are correlated. We could, and many people do, perform data assimilation calculations while assuming that the benchmark measurements are completely uncorrelated, but assuming that each measurement is completely independent allows each experiment to contribute more information to the adjustment process than it actually has. For example, if we take this to the extreme and enter the same exact experiment twice in the TSURFER input, then TSURFER would give this one experiment twice the weight that it deserves, even though its results are completely 100% correlated. Thankfully, TSURFER allows users to enter experimental benchmark correlation information if you actually have it. Determining and generating this experimental correlation data is not simple. It's actually the subject of several ongoing international collaborative studies. Another disadvantage, or at least a question about data assimilation methods, is how do we know that their data adjustments have converged to the true adjustments for that data? We might have hundreds to thousands of criticality benchmark experiments to feed into TSURFER, but we'll have at least several thousand high-sensitivity cross-sections to adjust, and tens to hundreds of thousands of marginally sensitive cross-sections also to adjust. If we decide to adjust our resolved or unresolved resonance parameters directly, which is a subject of ongoing research, then we have hundreds of thousands, if not millions, of highly sensitive nuclear data parameters to adjust. So even under the best of circumstances, we're dealing with a very under-constrained problem. So it's important to know if our data adjustments and bias estimates are reasonably converged. It's difficult to know if these estimates are converged. However, studies by Perfetti have made good progress into this. In these studies, I started with 56 completely uncorrelated critical benchmark experiments and changed how many experiments were included in a TSURFER calculation. For each number of experiments that I included, I randomly sampled which experiments were included, and the distribution of the bias estimates allowed me to draw a heat map showing how well converged the bias estimates were. In some cases, the bias estimates quickly converged around the final bias estimate that used all 56 experiments, and in other cases, the bias estimates oscillated between two bimodal results, suggesting that the bias estimates were having trouble deciding which one of these two biases to converge to. These kinds of convergence studies take a great deal of time to perform, but they provide an effective means for knowing if TSURFER calculations use enough benchmark experiments. We haven't performed enough of these convergence studies to develop best practices for these methods, but this is something that we could certainly do in the future. Another disadvantage to the TSURFER method is that we might not be adjusting every piece of nuclear data that we need to adjust. High-fidelity data adjustment calculations should adjust every piece of data that could contribute to the bias. If we're not allowed to adjust everything that could be causing error, then we're effectively over-adjusting some other pieces of data to compensate. Modern sensitivity calculations allow us to estimate the sensitivity to almost all of the uncertain nuclear data, but one thing that we don't usually adjust is the angular scattering moments. It's not difficult to compute the sensitivity of the eigenvalue to this data, but most codes don't have this capability just yet. What's more, the covariance data for the angular scattering moments is not widely available, and it might not be of the highest quality since we haven't tried adjusting it yet. But in theory, we could adjust this and all other missing quantities. The last difficulty with the TSURFER method is that we don't have a clear understanding of how to use it to estimate USLs. Should the USL just require that the adjusted K-effective plus 1.644 times the adjusted uncertainty and all appropriate margins be less than 1? This makes sense if the TSURFER adjustments are correct, but we don't know with absolute certainty that they are correct, and we don't have a confidence level for their predictions. Thus, it is difficult for TSURFER results to produce something like a 95-95 confidence interval, which makes criticality analysts uneasy about the method. What's more, the SURFER post-adjustment nuclear data-induced uncertainty is generally much smaller than the pre-adjustment uncertainty. It's usually around 0.25% delta K over K, which means that SURFER tends to produce fairly high, non-conservative USL estimates if we use this formula. Higher USLs make people nervous, which makes some people feel uneasy about using this SURFER method to determine upper subcritical limits. Nonetheless, I feel that the SURFER method is the most mathematically rigorous of the USL methods, and that it has great potential if we can resolve these standing questions surrounding the method. We'll close today by walking through a sample SURFER calculation. Like most scale codes, you can generate a SURFER input and run SURFER using the Fulcrum GUI, and the first and second lines of the input are just the sequence name and the title of your job. The SURFER input contains some parameters that tell SURFER how to run its data assimilation calculation. Some common input parameters include print adjustments, which tells SURFER to print its final cross-section adjustments, chi-squared filter, which tells SURFER which of the outlier filtering methods to use to identify outlier experiments. The default for this parameter is the delta chi-squared method, which is again the most rigorous, but also most time-consuming approach. And then lastly, we have target chi, which provides the chi-squared cutoff for the chi-squared filtering method. Increasing the value of this parameter will make it less likely for SURFER to filter out any specific outlier candidate. From here, we provide SURFER with a list of the SDFs that we want to use for our target applications and for our benchmark experiments. We can either enter the benchmark experiments and the applications using the read applications and read experiments cards, just like from Tsunami IP, or we can use the read response block. If we use the read response block, we can put both the applications and the experiments in here together, and the use equals keyword tells SURFER if we're using one case either as an application or as an experiment. SURFER will default to using any SDF as an experiment if we don't enter the use equals keyword. For all of our experiments, we'll also want to enter the EV equals and the UV equals keywords, where again, just like for Tsunami IP, EV provides the experimental K-effective, and UV provides the uncertainty in that value. From here we can run SURFER, and then open the output file. Here SURFER will provide a list of the initial responses that we entered, and it's always important to check that these values match what we think they should be. SURFER will also summarize the adjustments that it makes by response, and also provide a description of the adjusted responses, where these values are all the K adjusted for our benchmark experiment and application cases. SURFER also provides the standard deviation for these adjusted K-effectives in this output. Next, and perhaps most importantly, SURFER will provide a summary of the application biases. Again, SURFER outputs the initial values for K-effective for these applications, the post-adjustment values, and also the bias and the residual uncertainty in these biases. SURFER will also print the adjustments that it made to the different cross-sections, but it's perhaps more informative to look at these adjustments visually. Before we do that, let's look at the adjustments to K-effective that SURFER made. We can do that by opening the .keffectiveadjust file, and then double-clicking the document setting to plot these adjustments. You may have to adjust the y-axis scales to make all these points and their error bars be visible. In this case, I don't adjust it far enough, so you can't see the K-effectives for the first two responses, which are again our applications. But for the other ones, you can clearly see the initial K-effectives and the adjusted K-effectives. Next, you can plot the cross-section adjustments by opening the XSAdjust file. SURFER will barf up a whole lot of adjustments in text format first, but with a little navigation, you can find a list of the different isotopes and plot their adjustments individually. As you can see, SURFER provides information on which cross-sections should be adjusted the most, and how these cross-sections should be adjusted as a function of energy. This is a quick demonstration calculation, and so these adjustments don't provide any meaningful information, But if you use enough high-quality benchmark experiments, TSURFER can guide nuclear data scientists on how certain cross-sections need to be adjusted. Unfortunately, these adjustments are still in the multi-group form, but my students and I are currently working to extend TSURFER into the continuous energy adjustment realm. This concludes our lecture on the TSURFER data assimilation or data adjustment method. Again, the TSURFER method provides perhaps the most mathematically rigorous approach for reconciling differences between the calculated and observed experimental k-effectives, but then again, it's also the least applicable method for computing USLs, or at least it's a method around which we have perhaps the least experience with computing USLs. We have discussed pretty much all of the modern USL estimation methods in this course, and each of these methods has its own advantages and disadvantages. I hope that you found this information informative and that you've learned enough about each USL method to pick whichever one is best suited for your application. In the next and final lecture in this course, we will discuss preparing criticality safety evaluations.